We will now shortly come back to an example of isomorphisms that we already partially saw. So if C is a category, then we can form another category denoted by C iso, and it is defined as follows. The collection of objects is the same as it was for the category C, but the morphisms between two objects are now in general only a subset of the morphisms in the original categories. So the morphisms in C iso from A to B, these are all morphisms in our category C that are isomorphisms. And with the observation that the composite of two isomorphisms is an isomorphism again, and that the identity morphism is always an isomorphism, basically by definition, one sees that this C iso is a category again, and it's actually an example of what is called subcategory of C. So in general, a subcategory of a category C is a subcollection of the collection of objects, and then for each pair of objects in the subcollection, the set of homomorphisms in the set category is a subset of the homomorphisms in the original category, in a way that the identities lie in these subsets of morphisms, and such that the composition of the original category restricts to the subcategory. And the category of isomorphisms here is just an example of such a subcategory, and it's a somewhat special example in the sense that it contains all objects of the category. I'll now come to a category theoretic generalization of the concept of injective and surjective maps. And the definition for this is as follows. So let C be a category, and let F from A to B be a morphism in the category C, then we say that F is monic, or we also say that F is a monomorphism if for all pairs of morphisms G, H from some object X to our object A, with the property that the composites Fg and Fh coincide, we have that G and H must be equal. So this is a definition, and the point of this definition is only to use the structure that is present in an arbitrary category. So when I said this generalizes injective, one would think that this again is something about elements, but well, in general, an object in a category does not come with a set of elements. So this is why we need this category theoretic notion to generalize injectivity. And I'll explain, of course, in a second why this can be viewed as a generalization of injectivity. So then there is an analogous notion. So we say that F is epic, or epimorphism, if for all morphisms D, E from B to some object Y with the property that if we take first F and then D, and first F and then E, and so whenever we have that these two composites coincide, then it follows that D equals E. Okay, this is again only using notions that are present in a general category. Let's look what this means in examples. Our first example is the category of sets. So in the category of sets that I discussed earlier, we have that monic is equivalent to injective. Let's briefly check this. The implication injective implies monic. This is in fact easy because if these are maps of sets and F is injective, then we can cancel F here by the very definition of injectivity. And now let's look at the other implication. There we are faced the following problem. If we have that F of A and F of A prime equal for two possibly different elements of our set, then we have to show that these elements are in fact the same. And to see this, we now consider the one element set X and the functions G, H from X to A that are defined by G of X is A and H of X is A prime, then this equality here implies that we have D Fg equals Fh. So now if we assume that F is monic, it follows that G equals H, but if G equals H, we have that A equals A prime. In this way, monic implies injective. So then let's look at this second part of the definition. And here it's true that in the category of sets, we similarly have that epic is equivalent to surjective. Again, it's easy to see that surjective implies epic, because if F is a surjective map of sets, then its image is all of B, and so D and E coincide on all of B, and they are equal. That was easy. And the other way around is also easy. We have, again, to bring ourselves in a situation where we can use such test maps. And what one can, for example, do is one can consider the set Y that consists of the complement of the image of A and the disjoint union with one element that we simply call Y. And now we look at the map D and E from B to Y defined as follows. Well, we set D of B to be Y for all B in B, and we set E of B to be B if B is in the complement of the image of the map A and Y otherwise. These are two well-defined functions between these two sets, and one checks that if we pre-compose them with F, they will coincide. They will both be the function with constant value Y. So if F is now an epimorphism, it follows that these two functions here coincide, but this shows that this set has to be empty because there cannot be an element mapped to something that's different from Y. And so this way we see that epic implies surjective. Okay, so in the category of sets, epimorphisms and monomorphisms are generalizations of injective and surjective maps. The situation is very analogous in the category of K-vector spaces. Here we also have that monic is the same as injective, and we have that epic is the same as surjective. I'll not really go into the proof, but maybe just mention the last implication here. So epic implies surjective. So if f from A to B is homomorphism of vector spaces that is epic, then you should consider the following situation. So you should compose it with a projection to the quotient space of B by the image of A and the trivial map here, and you will be again in a situation where these two composites coincide, more or less by definition of the quotient vector space, and the requirement in the definition of epic maps says that these two have to be the same, and this exactly means that the image of F has to be all of B. So in particular, we now note that both in the category of sets and in the category of K-vector spaces, it's true that a map is an isomorphism if and only if it is both epic and monic, because we just saw epic and monic in these two examples implies injective and surjective, and we know that injective and surjective together in these two examples implies that maps are isomorphisms. This may lead one to the idea that it might always be true that epic and monic implies isomorphism, but this is not at all true, and I'll now present an example that highlights this phenomenon. So to see this, we now look at the category of rings. So this is unitary rings and ring homomorphisms. And in view of all the examples we saw so far, it should be obvious that this is a category here. And the homomorphism we are now interested in is the following. It's the inclusion of the natural numbers in the rationals. And I claim that this is a morphism that is not surjective. Well, this is certainly easy to see, but it is in fact an epimorphism, so it's epic. And to see this, we will now give ourselves two test maps, D, E, from the rationals to some other unitary ring, with the property that if we take first the inclusion of the integers, then these maps coincide. And the claim is now that this does indeed imply that V equals E, and this can be done by a very simple calculation. So if we have a fraction x divided by y, then we can do the following manipulation. It's d of 1. So if we apply d to x divided by y, then it's d applied to 1 divided by y times dx, which is now d1 divided by y ex by this requirement here. This is now in turn the same as d1 divided by y times e of x times y times e1 evaluated on 1 divided by y, which is then d of 1 divided by y d of x, y, e, 1 divided by y, and now using once more this relation here, we see that this is the same as e evaluated at x divided by y. And this calculation shows that d equals e under this hypothesis here, and by definition of an epic map, this implies that I is an epimorphism. And it is also not difficult to check that I is monic, so it's a map that is both epic and monic, but that clearly fails to be an isomorphism in the category of rings. So I'll write this conclusion down because it's important to keep in mind. So the corollary is, it is not true that epic and monic together implies isomorphism.